Okay, welcome back. And as promised, today we're going to start talking about classes. This is lecture 3, not 2. I'm going to still finish up lecture 2, but lecture 2 is a little more difficult. Lecture 3 is all about classes and hierarchies and inheritance and all class concepts. So I actually like this lecture as a starting point better, but I will eventually go back to lecture 2 and cover that second half, or third half, I should say. But just in case you're following along with the PowerPoints, what we're doing here is looking at how to create and use classes in terms of their effectiveness. So what I'm going to talk about today is the terminology, file topology, designing classes, functions inside of classes or methods. That's why normally it's good to know how to create a function, which is the first assignment for this course. They're talking about as well the concept of the constructor, the concept of the accessors, the modifiers, and miscellaneous concepts associated with those methods, and then the driver and the object instantiation and those particular concepts. And then next week we'll talk about inheritance. So I'm not gonna bombard you with everything about classes today, but we'll start out with the basic concept, and then next week we'll build upon it. If you're familiar with Java, it's very similar in concept. Except for we don't have to create a class in C++. We have to create one in Java. So in terms of the terminology, now we're in object-oriented land, because until you create a class, you're really not working with object orientation. So in object orientation, real C++ programs, they create classes and they use them. So the class is a combination of data and functions. It's not a program. Instead, it's the implementation of an object. So we create objects by writing classes, and we take those classes and we use them in combination with other classes to get the functionality provided, to provide the functionality we're interested in doing. So it creates a new data type as well. Last time I was talking about different abstract data types that are created by the user, structures, type defines, and stuff like that, enumerations. So the class is another abstract data type, and it's a generic description of an object in terms of a template. And several class instances can be created. So we have these different types of objects, object types that are instances of different classes that we create in our programs. Each instance has its own variables. They don't share variables. We can also have class level variables in C++. So we have instance variables and class variables and instances of objects. And then the objects, they hold data, but they also have functionality associated with them. So functions are now called methods or behaviors, and we don't use the word, rarely do we use the word member functions, but we could call them member functions as well. So, in terms of the topology, what are we looking at? Actually, hold on one second. I think my computer is doing something. Not quite sure what. Yeah. Just wanted to make sure I was still recording. Alright. I saw a little round thing come up, and I'm like, oh no, this happened the other day. Okay, so let's talk about the file topology. In Java, it's really easy. We just create a myclass.java file. In C++, we have different files that we create in terms of what it is we're trying to accomplish. And here, what we're looking at is a driver in the middle. So in the middle here, we have this box that's in green. And we call it a driver class, a driver program. It doesn't actually have to contain any classes at all. It can contain regular old imperative code with functions and methods and, behaviors that we're going to do in order to exercise the classes. So the driver is where we create the instances, and we're going to talk about dogs and cats in terms of objects for this particular program. So the program is going to have some dogs and cats in it, and then we're going to inherit the dogs and create different types of dogs next week. So what we have then is a separate kind of concept of a cat, separate concept of a dog, and inside of dog.c++ we have a description of what we would call a dog. Inside of cat.c++ we have the description of the cat, and then the person, description of a human being, all kind of controlled separately in terms of their identities. And then in the driver, and I like to call it a driver program. Some people like to call it main. It's the program that's going to have the main function in it that's going to start the program. So we make instances and then we tell them what to do, which is really the controlling program or the controlling driver of the entire application. So we got a couple rules. The classes usually begin with an uppercase letter, so capital D-O-G, capital C-O-G, C-A-T, in terms of the file names. And the name of the file that you put the class in should be called the name of the class.c++. In Java, that's an absolute must. In fact, you won't be able to compile it unless the file is actually called the same name as the class that's defined inside of it. In C++, not a must, but a nice naming convention, nice way of doing it. We don't actually have to use capital letters either, but it's nice to follow standards. So especially if it's a public class later on, we want to make sure that we can identify things easily. It just makes it easier to find the files, because if everything's kept in a separate file, then it's, if we label them properly, we actually know which class is in which file. So if we want to, however, in C++, we could put them all in the same file, and it compiles just fine. It's a little bit not quite as strict as Java. Here's an example. If we want to create a dog, then we should name the class dog and put it in a file called dog.c++. Remember, C++ is case sensitive in terms of our file usage. So here's the smallest class. It's kind of going to be like our hello world class. It's just empty, and it's a template. So it has a template class, and then what's in red is the word that's the keyword that's being used to declare the class. So this looks very similar to Java, actually. Class, and then the class name, opening and closing brackets. Example, you're told to create a class X. We could go class X as a solution, opening and closing brackets with a semicolon at the end. Remembering there should be a separate file called x.c++, not capital letter x.c++, not a lower level. So in real life, in terms of a real life example, let's say we want to create our first class. And the class, we want to call it CDog, because we're creating a C++ dog implementation. And so we have the attributes, or the characteristics, the information or the data that the class is going to hold. And so we have, we want to know if the dog is rabid or not rabid. If it's a kind of a disease where they go crazy. So, and we're going to make it a Boolean type. It's going to be a yes or a no. And then the weight of the dog in integers or floats or something. And then the name of the dog. We can give our dogs names. And then we're going to have some behaviors, which are going to turn into our methods or our member functions, which are going to be growl, eat. I guess we could put the dog to sleep, run. Classic dog behaviors. So we start out in step number 1 by creating the skeleton of the class. And this is how we would declare the class. And we would put this in a file called CDog.c++. And we would just say class space CDog, opening and closing brackets. So all the attributes are going to go in there, and all the behaviors are also going to go in there in step number 2. In step number 1, we're just going to essentially draw out the template for the starting point. Now let's add the behaviors, and the behaviors and the attributes can go in any order. You can put the attributes first, behaviors second, or switch them around and put the behaviors up first. And behaviors are our member functions or methods, and these are going to be our data attributes or data variables. I like to actually put the attributes first. And this might look a little kind of a different syntax from Java, but we have public, private, and protected. And public, essentially, when we say public, everything that falls next in line is public until we see private. If we see private, then it switches from public to private. And this is going to be what's referred to as our access methods. So our access methods say that public is available to everybody, inside of the class, outside of the class, and where our primary audience is in our driver program. So in the driver program, we can change the value of rabid, weight, name. We can actually get at those members. And what we're doing here is just listing out, just as if we were to write any ordinary C program. These are data, so Boolean, rabid, integer weight, character name. We could use string for name, I guess, if we wanted to. And we could put includes up here at the top of the file, because what we're going to need to do is essentially the same thing we do when we write any C++ program, is run functions, run method calls or something inside of libraries. So the next thing we would do is kind of like look at the behaviors. And the behaviors are going to be facilitated somehow. Actually, a little note to kind of just clarify this public-private stuff as well. by default, we always make our member functions public and we keep the data private, which is kind of the same rule for Java or for other object-oriented languages, because seriously what we want to do is try and protect the value of the data, the assignments. So in some cases we don't want the user out there changing rabbit, because maybe the dog can only get rabbit in a certain way, and we want to make sure we run those member functions, which we haven't seen yet. That's going to basically change that value. So we have what's called get and sets, and if you're in the Java course, this is the same concept. You know, set rabbit, get rabbit, to basically alter or manipulate the data members instead of making them public. When we get into inheritance, we'll see that. But for right now, we're just going to make them public because it's a little easier to work with in terms of the demonstration. So we have the concept of the constructor in C++, the same concept that we have in Java. In fact, in Java, we just have the constructor. In C++, we have the constructor. We have the copy constructor, and then we have the destructor. It just takes and removes memory that we've allocated, because we can use allocated memory, we can dynamically allocate memory in C++. We can't do that in Java. So let's start out with the constructor concept, and I'll wait with the copy constructor and the deconstructor for another lecture, because really until we start looking at memory, dynamic memory, allocating stuff, we don't really need to worry about it. So the constructor is a special function that's used to initialize all or part of the data members that we've looked at, and it activates when someone creates a new instance of a class. Same behavior as with Java. So you make a new instance of this particular class, the constructor goes off automatically. The constructor, with the proper number of parameters that you've given it, will automatically invoke itself. So the name of the function must be the same as the name of the class, same rules we've seen in Java. And the constructor will vary depending upon the design. So you can ask some questions: are all dogs born either rabbit or non-rabbit? Yeah, usually they're all born non-rabbit, hopefully. And are all dogs born of the same weight? Probably not. And are they born with the same name? Probably not. So maybe not all of the data members can be set, but some of them could be set. So if ever there's a no, you need to have information passed in terms of parameters to the function. And here's our constructor. Now this is interesting to note because it's a little different than Java. Actually, we don't have the scope resolution in Java. So notice that every CDog that we're going to create here will be born non-rabbit. Rabbit is equal to false. And the name and the weight is going to be entered in from parameters that are going to be sent to the constructor. This was not what I would consider a default constructor. Normally a default constructor has no parameters and it just sets information for us automatically. And there's no requirement, we don't have to have a default constructor. We can simply run with any constructor that we want. And interesting thing is we could leave this out and it would actually work because it's being defined inside of the class. But what we're going to see in coming up slides is that we can separate the abstraction of the implementation from the specification. And if we're doing that, then we have to do this, because we're saying inside of CDog, look at the CDog method, and in that particular case, you know, here's the method body and here's the implementation that we would do on a specification. And I'll talk about that in a few minutes so you can kind of see, but start to get used to the concept that you have to specify inside of this class CDog. We're writing this method CDog. And so what we can do in the future is, you know, alter a method that already exists inside of a class that we're inheriting from by using this. And this is nothing more than a scope resolution operator that says go look for it. Why? Because we're working with global scope and we don't have anything managing our scope like Java does. Instead, we have to actually decide, well, where is this from? Where is this coming from? Instead of using words like extend or implement or something like that, we're essentially using a scope resolution. And let's talk about the driver for a second. So we're talking about a whole brand new file. And the driver contains main. And it's in a controlling algorithm. So steps, what you want to do is type in the skeleton, create a couple of instances of the class, and then tell those instances something. So have create a couple dogs, create a couple cats, and have them do something. So here's our main. It looks like hello world, doesn't it? So this would actually go in a separate file, and we would call this my program or something .c++. And you type in the skeleton here, we're going to include iostream.h, and we're going to have void main. This is like any other C program that you've written so far, which is kind of different from Java, because Java we could actually put the main inside of a class, put it all in one .java file, and then we have one .class file that runs. We could actually do that if we put main inside of one of our class declaration files. We could run it, because what it's looking for is main as a starting point in terms of where the execution is going to start. If you didn't include a main, but you had some classes and you tried to run it, it would tell you there's no main. And then you create a main, and in your main you're going to put your instances of your classes that you're creating. But in C++, it's common standard to keep the main separate, put it in a separate program. So in step number 2 here, we're going to declare a CDog pointer. And now I'm going to start using pointers because this is twofold. I'm going to show you about classes, but also show you about pointers at the same time. And you notice that we have this this asterisk that came out here, and I said CDog space C1, which means we're creating a pointer variable called C1, and is of data type CDog, and it's a pointer variable because we're including this asterisk. That could be here. We could put a space, put it in between, or we could put it next to C1. It's common actually to kind of see this asterisk over here to say this is a CDog type data type, and it's going to be a pointer data type. So null essentially means that it's dead because we've allocated memory for C1, and this is sort of like, and I'll show you another way of saying new, which we don't have pointers in Java, which is kind of like why I'm pointing it this way, because some of you have taken my Java class and you're like, well, they can just say CDog is equal to new CDog, you know, or a new CDog, you know, and you can run it that way. Yeah, we can run it that way as well. We have both options, but this is what you haven't seen yet. But in terms of this pointer, it's a CDog pointer. It's going out and it's allocating memory. It's calling it C1 and it's pointing to a memory address, but we haven't put anything in there yet. That's why it's null. It's just empty. And then we have the new operator, which is doing the same thing. In C++, this is considered dynamic memory allocation. Every time you use new, you're creating a new piece of memory. When you use delete, you're deleting the memory. So new brings instance to life, creates a new existence, calls the class constructor, and it opens up the memory space to fit the instance of the class that you're creating. So in terms of our syntax, what we have is the class, in our case CDog, with the asterisk and the variable name. We called it C1. And now we say C1 is equal to new, the name of our class, CDog, with any parameters. So we see in the next line, here we go. We have new CDog, C1, this is what we had before. And now we're saying C1, because we already have a data member, we already created a pointer variable of type CDog and we called it C1. So we're saying C1 is equal to new, which is creating our instance here. CDog with the weight 14 and the name Bob, because our constructor that we created had a name and it had a weight associated to it. And down here, new calls the CDog constructor, and here's our constructor repeated so you can kind of see what it's doing. Sends integer x. So our weight's in integer values, which means our dogs always weigh whole integers. There's no portions. And then character y is going to be our array that we're assigning to the Bob, to the name. And we're going to call this. And we're going to say rabbit is equal to false, which is, this is our constructor. And the weight is equal to x, and name, we're going to string copy name to name what we put in as character array for y. And this string copy is part of the string.h library, and it's used to manipulate string variables too. Because you can't say one string is equal to another string. We have to actually copy. We have to use a method to copy it. Now, you know, those people are familiar with Java, you know, we have the string class. String, this is equal to that. This is, we don't have this string copy or string find, string rename, string concatenate, which is a little bit more detail. You have to run a couple of different methods in order to do the same manipulation. So what happens when we run this? We end up with a C1 that opens up, because we have 3 data members. We have the weights, we have the name, and we have rabbit or non-rabbit. So out here in memory for C1, this name memory space that we have here by this variable, new is creating 3 new memory locations. Nothing is created until we actually run it. and so it's allocated at runtime, which is why it's considered dynamic. Because when this program got originally started by the runtime environment, we didn't create it automatically. It got started when we made an instance. So we've dynamically allocated 3 spaces in memory to hold the 3 pieces of information. So we've passed the data 14 and Bob, we've passed in as the parameters. If familiar, it's the same concept with a method, because this is a function, and these are function parameters. So we pass this information in, and then it gets assigned. And now out in memory we have rabbit is equal to false, and then weight is 14, and then the name is Bob. So that's essentially how and it's actually stored sequentially, so that's how we can use the dot notation to kind of get at the dot name, dot weight, dot rabbit, to kind of get at the values that are associated with it. So now we're going to declare another CDog, and now this should look familiar. We've said no pointers at all this time. We're just going to create a variable, and we have CDog C2, and we're making 7 and 14. So the new dog's name is Ethel, and the weight is 7 pounds now instead. So when we do this, we actually in one shot created a variable called C2, allocated the memory, and assigned it. So what we're looking at here now is C2, which is another space in memory, and we've got the same information that's associated with it. But this one isn't a pointer. This is just a regular old. This is a regular old object that we created called C2. And when we pass it the values for the x and y, we end up now with false 7 Ethel. So we have 2 separate memory locations that are allocated, one for C1, one for C2. And 2 different ways of actually creating it, using the 2 statements of creating the pointer, taking the pointer, making it a new, or just creating a regular old variable without using a pointer. So you don't actually have to use pointers in this. If you use a pointer, you can allocate and deallocate. If you don't use a pointer, you can't deallocate. It's not dynamic. It doesn't happen at runtime. Instead, it happens, the memory space is allocated at compile time. And you have less control over what you're doing with it. And what you're doing with it is just making a copy of it, moving it, deleting it, manipulating it from a pointer perspective versus a regular old variable. Which for your instances right now, for your purposes right now, there's not really that much utility to it. But so back to CDog. Inside of CDog we had the constructor here. And the constructor we've looked at, and we've made a couple of instances of it. Now we can add behaviors. We need to add behavior to eat, growl, sleep. We can essentially make this dog do whatever it is we want it to do through programming. And so now we're going to follow the same pattern as we did with the constructor. And we're going to call these void in terms of what their return type is, because these are nothing more than functions, although we're calling them methods now. So inside of the CDog class, we're writing void CDog, and then we're using the same scope resolution operator as before, and we're saying eat. And then what are these going to eat? Well, it's going to print out that the dog's name is eating now, and then we're going to increase the weight because he's eating, right? So he gets a pound every time or something. And then CDog growl is just going to print out growl, let's say, to the screen. And so this is what it looks like after we've added the methods. And so we have the constructor up here, and then we have the 2 methods that we've added, one to eat and the other one to growl, which is kind of interesting. Think about it. We have those methods on there. And now let's take a look at this dot notation. In Java, we had just the dot. In C++, now we have the dot. And what is this? This is a line and I'm sorry? It is, yes. It's the this operator. But we actually have a symbol for it. It's actually 2 characters. And I did, believe it or not, this is why I'm saying it, I did, believe it or not, have one student tell me, where is that on the keyboard? It isn't. It's the minus and then it's the arrow. It's 2 characters, not 1, but it looks like 1 character when you write it out. And okay, when do you use this one then? They're used for the same purpose, but in 2 different instances. This is used when you're not using pointers. This is used when you're using pointers. Why do we have 2 separate ones? I have no idea. Seriously, because you'd think they'd be able to build it into the language and say it would know whether it was a pointer or if it wasn't a pointer. But I don't know. If you haven't used this one before, you probably haven't used pointers. So we created that first C1 dog, we created as a pointer. Well, for the purposes so I could show you this operator. But the C2 was just a regular old C2 instance. So we can use the dot notation because we haven't used a pointer. So the dot operator is used for non-pointers. And what is it? It is to get the instance attributes, the instance methods, or to basically go inside of the class and access something inside of that class implementation. Same thing that you would use it for in Java. As an example, we have the instance dot, an attribute, or a method. And then if we're going to use the arrow operator, it's used for pointers. If we're going to use a pointer, we have to do this. If we use a dot on a pointer, we get an error message that comes back. So it's the same format, same usage as before, but we put the no dot anymore. We put the line and the arrow instead. And it gives us the same results, actually. So using the dot and the line arrow operators, we have here C1, which is a pointer variable, and we have C2, which is not a pointer variable. So C2.bark and C1, and with this new operator that gives us a growl, because we run the method growl. This is probably the only thing that confuses people, I would say, in terms of the dot notation. When they start moving from Java to C++, it kind of goes, hey, what about a pointer? Java, it's all the same. Actually, you can't create a pointer in Java, so you don't ever have the symbol introduced to you before. So let's talk about accessors and modifiers, and we'll look at some more examples. Same concept as Java, actually, to access and modify data members, but if you don't know Java, and assuming you don't, let's discuss the concept briefly. So the accessor is a method that returns the value of an attribute. Will have a non-void return type because it's returning something. And has a return statement inside of the method at the end. And a modifier is something that changes a value. So accesses gets it, modifies change it, but doesn't return it. So the change is based off of a parameter list, and it has void as the return type because it's not necessarily going to return anything. Instead, it's going to modify a data value. So it's one accessors and one modifier per attribute normally. Same kind of standard that we see in Java. So here's the accessor for the rapid attribute, and this is going to be getRapid. And this is really where the get and the set started from. It actually comes from a C++ sort of syntax. So we have Boolean as the data type, and rapid is going to be true or false. So instead here we're going to get it, which means we're going to return it, which means this is going to give us the rapid, and then we can take and we can print it to the screen if we want. We can say a cout get c1.getRapid, and that would print out true or false to the screen. And then the modifier here, void CDog setRapid, is essentially going to take on a Boolean, my Boolean, which is going to be a true or false. And that's going to say rapid is equal to my Boolean. And we don't have to return anything, so we have void here because we're just going to set the value. So put these inside of the CDog class along with everything else, and we can run it. So out there in main, in our driver program, we're going to use it, and we have C1, and then because we're using a C1 as a pointer, so we're using the pointer dot resolution, set rapid 1, and then cout get rapid, and prints out 1 to the screen because that's what the value that we've set the rapid to. So it's going to print out true, I should say, to the screen. And that's the interesting thing about C++ is we do have the Boolean operator, the Boolean data type, so we can set true or false with 0 or 1 to correspond to true or false. So we can make a separate header file now. The header file is referred to as the specification. So we can specify what we would like this particular class to contain, which is why in the implementation, what we've seen so far, we've been using this dot resolution here because we're assuming we're going to make a header file out of this. And we have to know what header, what what method are we implementing inside of which class are you talking about? Which is why we use the scope resolution operator. We don't have two files in Java. It's a C++ thing. And it follows the same pattern as this. This is a header file, iostream.h. We include iostream.h, and we call the methods that we're using, like cin, cout. And we don't worry about the implementation. We have the specification for the methods that we're running, or for the functions that we're running, and we are just running them. And when we compile it, the compiler takes the .h, finds the precompiled object code that we have, which is why those are referred to as precompiled headers, and it links the object code for iostream.h with our object code that we've created from our my program. And the compiler does all of the put this in here, put this in here, put this in here, and puts it all together. So we don't have to recompile iostream.h every time we compile a new program, which is why it's pre-compiled. So it links the object code. Well, we're going to do the same thing with our classes, because why do we want to, every time we compile a program, why do we want to recompile all of our classes? Unless our class changed or something, and then we can recompile the class. And the compiler will check for that, actually. In fact, it'll check for your C++ file too. If you accidentally change something, one of the header files or something, you go in there and you mess around, it'll try and recompile those precompiled headers as well. But you don't want to do that. Leave your built-in classes alone. So we want to make a separate header file, and inside of the separate header file, for a generic description of CDog, we're going to have public. Right now we're just using public for everything. Weight, rabbit, name, same thing as we had before. Here's our default constructor, and here's our assessor and our modifier, our get weight, set weight, get rabbit, set rabbit. And notice we don't have anything. These are what's referred to as function prototypes or method prototypes or specifications. If you're talking about C++, void, bark, semicolon, no opening and closing brackets. So if you're familiar with function prototypes, that's what you're putting into the header file, which means every implementation off of the specification must implement all of the headers functions, prototype functions, methods, which means if it's in the header file, it must be implemented in the implementation of the .c++ file. So here's our final CDog.c++ file. We have CDog.h, and it has in there, it's got all of the all of the functions. CDog.c++, it's got the constructor, it's got, well, we've got ceat, cgrowl, and the implementations where we have CDog, where we've implemented it. We can also implement it in the, if we know that the behavior is going to be the same, we can implement it in the .h along with the specification and not actually have to make our user re-implement it all over again. For example, if we were going to create a CDog and we wanted to know every CDog is going to have a rabbit set to true or something or false, we can go ahead and set it in the .h file, and so we don't have to reinvent it or set it again. But in the CDog.c++ file, I knew that was going to trip me up. We can set our constructor, which our constructor is not going to be in our .h file, because we're implementing the constructor. We're having the behavior happen automatically for us. So here we have the get, the sets, and all of the different behaviors for the for the different behavior that we have specified. So summary of the class concept: the class is the generic description, which is why we have many different instances of the class. And when creating it, we sketch the outline, we fill in the attributes, we fill in the constructor, and then we make the accessors and the modifiers and any other miscellaneous stuff. And the classes go in separate files. Each one of those classes are in a separate file with a capital letter for the class name. And the file itself has to be saved with a capital letter as well, if we were capitalizing the first character of the class name. And then we have the dot, and then we have this, minus sign and the arrow operators to tell us, that we want to run an instance. From the instance of each one of the classes that we've created an object of, we want to run a method or set an attribute that's associated with it. Now what I want to do is kind of switch lectures, because I don't want to talk about inheritance today, but I want to go back to this was lecture 3, by the way, and we'll finish lecture 3 next week with inheritance, but I want to go back to lecture 2 that I had started previously. Whoops, I thought I had it open, but I guess I didn't. Let me go find lecture 2. Here it is. And finish up with the concept of the class, and you'll see a slightly different, more higher level, I should say. Oops, where's my lecture? Maybe that's what failed before. Up there it is. We were slightly challenged a few minutes ago at the beginning of this lecture. Technology-wise, my computer was slightly challenged. So instead of sitting in the car and getting overheated and hot, instead it sat in the car and got wet yesterday. No, just kidding. It did not get wet. This particular lecture was talking about all these different data types and abstract data types, enumerations. We were talking about structured ones, and I started talking about structures and unions, and I ended with class last time. So I'm going to pick up where I left off and talk about the class concept. And the information is slightly different, although it's similar. This actually kind of comes from 2 separate sources, but each one of them kind of displays it in a slightly different format. I went through unions, right? Yeah. Okay, good. Make sure I went through the concept of unions. What is a union? It's the same thing as a class, but same thing as a structure, but it only uses one data member at a time. So, yeah. Type defines, structures. I believe I stopped at classes, information hiding, the concept of, and then I think I stopped here. Okay, good. So now, if I showed you this at the beginning, you'd go, whoa, this is a class. So, a little higher level, as I mentioned before. All right, so what do we have now? We have the specification file. This file is called timetype.h. And in timetype.h, as I mentioned before, we have all of our function prototypes, which means we're going to have something called void write, and the keyword constant says we can't change it, we can't overwrite it, and I'll get into that in a few minutes. Void increment, void set, because we're not using a default constructor here. Instead, we've created a method called set to set our times, and in the last lecture I showed you, we had it all public. Excuse me, we had it all public. Here we have a public and a private section, and we've put our private data last. Now I've switched the order. As I mentioned before, we can put the data members on top, member functions on the bottom. That's actually what I like, but some people like to do, in this particular author, and this is coming from the slide set from the textbook that I recommended for the course. He likes to put the private on the bottom because the private never changes, and we don't have to be concerned with that, apparently, because it's private. Which means, if it's private, it means it can only be looked at inside of the class. You can't modify it outside of the class. So we have a separate section, private. You don't have to put a space here. You can put the colon right next to the word. But the private, generally, you'll see come second, and the public come first. So he's organized it by public and private. In terms of here, we have hours, minutes, and seconds, which basically defines a time type. Yes? This is in the header file. This file is called timetype.h. The compiler, when you include timetype.h, will go back and look at timetype.c++, which I'm going to show you next, and compile, if it's not compiled already, compile it to produce object code. If it's already in an object code form, take the object code. You don't have to compile it anymore. So they call this a specification because it specifies what's inside of C++. And this is easier to look at instead of all of the method bodies implemented. This is a lot shorter, a lot easier to look at. So we're declaring some data members. We've got 5 member functions, and we have 3 data members. So we're going to use this in terms of an abstract data type. So it facilitates reuse in C++ code. So software that uses a class is called the client. I called it a driver in the previous lecture, but it can also be referred to as a client code. Anything that uses it. Variables and types are also called class objects and class instances. And the client code uses public member functions to handle all of the class objects. So when using the class by concept, you're defining you're defining an identity of components or class members, class variables, functions, which we've seen so far. And the class members are normally private by default, the members of the data. The compiler doesn't permit client code to access private class members. So it's a protective mechanism. Same thing is true for Java, actually, but it's more seen in C++ because we have client code. In Java, we just have everything as a class. So we just think about it in terms of class to class, but the client code is generally the spot that's making, the part of the program that's actually making the instances of the classes, and that's usually the public interface, not the private. So we mark things private to say, hey, client code, you can't touch this. So class members are declared public. The members are the data functions because they provide what's referred to as the interface, the public interface to the class from the client code. In most cases, private members contain the data. The public functions manipulate that data, as I mentioned before. And then now we have the concept of the constructor, and this is basically the lecture on it, giving you the formal definition of it. We've seen it, but we don't actually have to have it. But it's a way of automating. So each new instance, the constructor gets fired, and we have the automated code that gets done for us. We also have this access function, or the observer. So it's a member function that can inspect, and it's not modifying anything, it's just accessing it. In terms of what I mentioned before, the accessor and the modifier. And the function is declared with the word constant followed by the parameter list in both of the specification and the implementation. And this basically says, here it is here, this keyword constant, and this is sort of new, I believe, to C++ versus Java. This says we're writing something to the screen, which means we are not allowed to change anything, which means through inheritance it's public, however it's not changeable. It's not modifiable, it's constant. And when that keyword constant comes up in parameter lists, it comes up in method declarations and prototypes, it comes up all over the place. That tells us, we've essentially implemented something in there that you're not going to change. It's constant. Which is kind of like making, a definition of pi 3.14 and keeping it that way. You can't change the constant variables themselves. So here we go. We have client code using time type, and here we're including time type.h, just the same way as we included iostream.h as an example. And we're going to use namespace. This should hopefully look familiar to you by now. And this is client code because we have integer main, going back to regular old non-object-oriented programming methods, essentially. So this is why I say that C++ is object-oriented, but you're still programming in an imperative fashion, because you still have a C program, essentially. You're still using this. This looks like, feels like, tastes like a C program. The only thing different is now we're making instances of objects in it. And so it's not an object, the driver program, it's a regular old program that we're running, which is referred to as our driver or our client code. However, we're using objects in it, but we don't have to use only objects. We can use other things. We can put a function in here, we can do anything we want. See, in Java, everything, even hello world, is an object, is inside of a class. So when you go from class to class to class to class, and you put a main in there to initiate something to get, and the main's like 5 lines long in Java. In C++, this is more than 5 lines. This is a lot of lines. This is the whole program running in here with some instances of some objects. Okay, so now we're going to declare 2 objects, and we're not going to use pointers in this example because I'm not going to try and illustrate the dot notation to you anymore. We're going to start a little lower level. So the time type current time and time type end time. And we have a boolean done, which is going to be equal to false because we're not done yet. And we're going to say current time dot set, end time dot set, which is running method calls as we've seen already. And then we have a little loop here for when we're going to check done, and when we're not done, when it's false. Time type dot increment. So we're going to increment the time, and then we have a method in there that we're going to implement that's going to increment, add 1 to the time. So if the time type is not equal to the end time, done is equal to true. Anyway, so we're taking the start time and making it equal to end time, setting up a timer for us, essentially. And this functionality is not part of any of the classes. It's part of the main program, or the client code that we're running. So the class declaration creates data types and names of the members and of the classes itself. It does not allocate any memory. So we can have a bunch of class declarations that we're using in our program. But until we make instances of them, we haven't allocated any memory, which is kind of different in the Java environment. When you load a class from a class in Java, it gets loaded into memory dynamically. In C++, it's not going to get loaded until you tell it to get loaded. And it's going to pre-allocate it at runtime. So all of the information that's going to be available for that memory allocation is on what's referred to as a stack or an activation record, because it's running in a Windows runtime environment. And it's already determined ahead of time how much memory your program is going to need and how much is going to be allocated to. So it doesn't actually grow the same way or expand the same way or load the same way as Java. So all of the classes have to be in the same location. They're actually all compiled together in the same executable file, which is kind of interesting, which is why we work with this object code in the header files instead of working with just like .class files. So the client code still needs to declare class variables. Two kinds of class variable members. We've seen this already, the data member and the member function. And we've seen this already as well. We have the private as default for the data, public for the members. And generally declared public, so we already got through that. We have some aggregate class operations that we can perform. So we have built-in operators that are valid on class objects, as we've seen. The member selection. So the member selection using the dot operator, or in our case of the pointers, we also have the line and the arrow. And the assignment to another class. So we can use the equals to assign an instance of one class to an instance of another class to reassign. We can pass to a function as an argument as well, by value or by reference. And we can return as a value of a function. So a class can be used in all of those different situations, or I should say an object. Other operations can be defined as class member functions. So here's some examples. So we have two separate class files that are going to be used for our class. And as I mentioned before, we have that .h file we just looked at in terms of the time type. And then in our implementation, that's going to be our time type.c++, where we're writing those method bodies. So it's just like taking, in the old days, a function prototype, putting it at the top of the program, and then somewhere at the bottom of the program, we've got our function that we've declared. But we've used our function before we've actually, the compiler's actually even read our function implementation, which is kind of the same concept with these .header files. We include the .h file. Then it goes finds, in another file, it finds the .c++ file. And we keep it separate so that we can use it in inheritance and modulation. So we can modularize out the functionality and then inherit it from it in future classes that we're creating. If we stuck it all in one file, which we can do, actually, we're not going to be able to inherit from that. It's all stuck in my first assignment for this class.com or something. It's stuck inside something. We don't see it as visually, so we separate them out into separate files so we can actually visually see through a directory listing what kind of classes we have. Then we can reuse them. So here's the implementation. We've seen the specification, but here's the implementation. This is the C++ file. And so we're including time type.h. So it also must appear in the client code. So it also, because we need to know, we have to include it in our implementation and our client code as well. And then inside of our implementation, here's where we're writing the code. So we have Boolean time type equals, where we can see if one time is equal to another time. It takes on two parameters. Or it takes on one parameter the other time. It's going to return something. And so what we're doing is we're implementing anything that wasn't implemented in the .h file. In terms of the member selection operator, this is another example in terms of how it's used, because what we're doing is we're calling, and I forgot to point out here, we have the scope resolution that says equal is inside of time type, because we have to go back and say, well, this is, where did equals come from? If we didn't use the scope resolution, we would be creating a new method and adding it to it called equals. And if we didn't implement all of the methods that weren't in time type, it would come back and say, hey, not implemented. Finish me up, you're not done with my implementation. And then we get at these methods through the dot notation, and here's actually kind of an example of a class that already exists, OFStream, which is for output streams. So when the client uses the public function, it requires the dot notation preceded by the object. So you can think of the function call as being sent to the object. So it's really kind of another way of running a function call using that dot resolution, which is kind of a different philosophy, same process but different philosophy with Java, actually, in terms of the way that's implemented. So a variable, an object, an instance can be out here. Dot open as a function call, dot close as a function call. So some of you actually have already used them in terms of the seeing, some of the functions that we're familiar with. C in and C out are actually objects, and we can run methods off of C in and C out that we haven't seen yet. So the member selection operator also gets at data members and also member functions. So the header IOStream and FStream declare IOStream, ISStream, OSStream, IFStream, all the different ones. Both C and C out are class objects, and the get and the ignore are function members inside of those class objects. So we've been using C in with directional operators to say read in, and believe it or not, those are operators for IO direction, which says it's the same thing as saying C in as a method call, which is what we're doing because those are objects, which is part of C++ because we're object oriented, which is why we use iostream.h versus stdio.h, which is the C equivalents to that, but those are functions, not methods. And so the stdio.h and C, you're running functions to fprint, scanf, and you're sending function parameters. iostream.h is the C++ equivalent to that. It's essentially doing the same thing, but they're objects, and you're creating instances of objects, and you're running methods on those objects. So you could actually say cin.get some character, or cin.ignore something, or cin.run the methods instead of doing the directional. Those little, for day one of the boot camp, I said, blow out the horn, suck into the horn. Those kind of, which are nothing more than redirection operators that say cin, cout, and use it with that. So it's a little bit easier for the new programmer who doesn't know object orientation to actually use those directional operators. Because when we start using the dots, we're going, wait a minute, that's an object. So iostream.h says, cin is an object, and dot something is running a method from that. So you don't have to know anything about object orientation to run cin and cout, which is why that's there. In fact, you can overload operators yourself and have the directional operators work with your methods if you wanted to. So statements below here declare my in file as an instance of a class. ifstream and invokes a method to open it up. So here we have .open as an example. So in the C++ libraries, once you start going through and using them, you end up having to figure out, oh, we have methods. And what you're doing is you're creating objects, instances of objects, and you're running methods on those objects, and they're built in C++ libraries. So instead of running functions, now you're running methods on objects in C++. So the scope resolution operator, here's your formal declaration of, in terms of your description of what it is. We've seen it in a couple of examples so far. Typically, there are several different class types. Different class types can write member functions with the same identifier, like write. So each one of our classes can have the same member function. So the member selection operator, or the scope resolution, member selection is telling us which method, scope resolution is telling us which class we're actually looking at. And we can do this with cin and cout as well. If we have different implementations of cin and cout, we can say inside of iostream.h, or iostream scope resolution operator cin, or fiostream cin. We can run different methods from different classes, or implement or overwrite. So the member selection operator is used to determine whose member function write is invoked. Current time.write or number z.write. And then in the implementation file, the scope resolution operator is used to in terms of the header before the function name to specify which class it's from. So in time type scope resolution, right? Because we can go all the way through the hierarchy and overwrite from different class levels, different methods that are inside of each one of the different classes using the scope resolution operator. So it comes in handy for a lot of different things in terms of overriding methods. Time type class instance diagrams is the same as I showed you before in terms of how the memory is being stored. Current time and end time have their own memory space with their own essential instance variables, which is why we call them instance versus class variables. So. And the use of the keyword, the constant here in terms of the member function, your formal definition of it is that it cannot be modified, so you use constant in both the function prototype and the specification, and in the header of the function declaration and the implementation. So it makes it so you can't modify it. So makes it constant. So. And here's the use of constant with the member function. So we have it right here. Void, this is what we saw in the first example actually, the word constant out here. So, and then we have hours, minutes, and seconds are essentially set for us. So we can't modify the implementation of write. It's just basically just going to write it out to the screen essentially. So in terms of our class constructor, the purpose of this is to initialize the private data member, same thing that we have in a Java environment. And the name of the constructor is always the same name as the class, so the same rules apply. And the constructor with no parameters is referred to as the default constructor. And we implicitly invoke it when we call it by giving it the same rules as before in terms of how we use it in Java. We give it the number of parameters. Depending upon the number and the type of parameters, it will pick the constructor that is supposed to be used for each instance. So here's our constructor example. The last one we didn't actually put a constructor in there. It's very common to see C++ programs without constructors for some reason. I think because the constructor concept kind of came along a little bit after the class implementation. We have some people who like to do their own, and you just call the method. Same, it's actually not considered a bad programming habit to write another method instead of using the constructor. But now we know about constructors, and it's a feature of the language. It's probably not a bad idea to use the built-in features versus creating it manually. But here we have our time type, which we have a constructor in here for hours, minutes, and seconds. And so in terms of our default constructor here, we can have as many as we want. We just put hours and minutes, hours. And we want to create one with just hours or something. So. In terms of the implementation of the constructor here of time type, the default one is going to say hours is 0, minutes is 0, seconds is 0. So. And because we're including this file, we don't have to redefine the variables that we're using. Kind of common mistake that a data member is identified in a .h file, and in a .c++ file they reinvent the wheel. They say integer hours, minutes, and seconds all over again. And it's like now you have two sets of variables. So you haven't really implemented the specification, you've created something new. Because you can add in the implementation something that doesn't exist in the specification when you've implemented it. And why do you have implementation versus specification? Because in this, which is kind of different than the Java thinking, in the C++ world, let's talk about time type for a second. We could have a specification file that says we have hours, minutes, and seconds. We can create different classes, implement different versions of this specification. One of them might just be regular old time, one of them might be international time. Maybe it has time zone on there. Maybe it has something added to it. Time and date would be a modification of the specification, but we have different implementations of it. Which is interesting because we only have to have one specification, and then we have, one specification, and then we have many different implementations of it that we can use. So we don't have to change the specification to provide a different type of time that we're going to use. Okay, so here's the time type constructor with the 3 hours, minutes, and seconds that are taken. See the automatic invocation of the constructor when we say time type departure time creates it with 0, time type movie time the 19, the 30, and the 0 end up being automatically invoked. So we have that going on. So here's our sample compilation and the linking of the files themselves. All of these files are included in this simple little program to create a time type. So we have the specification is the time type.h, and then we have the implementation over here, the time type.c++. The compiler compiles it. If we're in a C++ world, we got an obj object file. Some compilers actually call it .o these days, so for output. And then over here, this just stays the same. Once we've compiled this, we have the object code that goes into the linker. Over here, we've got a main program, and that gets compiled to client.obj or client.o. All this stuff gets into the linker to create client.exe. So once we have this already, we haven't changed it, we create another another client, we just link it. The linker essentially takes the object code and puts it together. So we don't have to go through and reinvent the wheel. So this is really what's referred to as pre-compiled object code, which is how all of the library files in C++ are organized. We just have object files, and the object files go through the linker. We don't have a linker in Java. The linker's in the runtime environment. So the JVM does the linking for us. So. But in a compiled format, we have the linker as part of the compilation process. We can avoid multiple inclusions of header files. So this is an interesting problem that ends up with C++, is that you have this file is included, that file is included, because we have a lot more includes. And when we include something, it might already be in something else that we're including. So if we have separate implementations off of the same specifications, we have multiple implementations that we're using, we might have the same header file included twice. Compiler's going to go back and say, hey, you already included this. Why are you including it again? Yeah, why load the same object code in twice when you only need it once? So often several programs are going to use the same header file containing type-defined statements, constants, all sorts of different things that can't be rewritten. So a compile time error occurs. So this preprocessor directive syntax is used to avoid the compilation problem, otherwise referring to as multiple uses of includes in the same header file. So you'll see this sometimes when you say, it's a hash line in definition, preprocessor, whatever, and we'll see an example of it in a minute. Define this, end it, which is basically saying in this definition, if we've already defined iostream.h, then leave it and don't redefine it, and ignore it. So you see that as the header here it is here, as the inside of the header, you'll see it inside of these files, which is again another C++ thing. Java assumes global scope. C++ is all local. So it goes out and finds it. Oh, look, you got this. Oh, look, you got this again. Oh, look. Oh, wait a minute. It's used in all of these different files. Compilation error. Which one do you want me to use? So you use this if in the definition. Skip it, essentially. So for compilation of class declarations, file time type.h will be included only once. So we have time type.h. Because in the client code, we've included time type.h. In the C++ code, we've included time type.h in our file. So out here, we've said in the definition, if we have time type.h, define time type .h, and whatever it happens to be called as an example. And then, here it is, and then leave it alone. It's already in the definition. Don't include it again. So you will rarely get this. You only get this if you have multiple uses of the same .h file. And if we have the dinosaur, which we do have, I think, as one of the assignments, we have a dinosaur program that you're going to create, you're going to run into this problem. So you have to go back to lecture 2, at the end of it, and see the syntax, and then you're going to cut and paste and put that in. I may have actually already put it into another example as well, though, that goes along with that project. So. And it's just the if in def. If you Google this keyword here, you'll see the syntax for it as well. Just basically listing out that if it's already in the definition, use it, don't redefine it, because it gets rid of the compilation error that might occur. So, do you guys want to see about inheritance today, or do we want to we're going to actually, I guess I talked fast. Inheritance?
It's hard to fast forward with regard to how you add the header file. Because when you add hash include to string.h, you put it in the small braces, right? The data sign and the smaller sign.
Usually you can put comments in there to say that why you're including this, why you're not including something.
Comment is
yes.
To hash.
Yes.
What I'm asking you is like hash include string.h. You put in this braces. In one of the slides you were saying you had a quote there, double quotes.
Double quotes says to look for it in the same direction. No, you're talking about whether or not you use these open and closing versus the double quotes. Use the double quotes if it's in the same directory. This is going to search in the directory tree, the hierarchy, to find it. I'm sorry? It starts at the root directory and searches down through the... If your compiler, it's a compiler specific thing as well. If your compiler properties allow you to specify include directories, like, you know, my C++ dash include, and then we have bin, and we have a bunch of other directories in there. If you can set the parameters up, you use this that says search at the beginning and go through everything. And everything's going to have, you know, an include directory, perhaps. Or it also says look for the include directory, depending upon how the compiler is set up. If you put the quotation marks, like in the later examples, you see time type and time type.h, and you see time type.h was probably in quotation marks instead of those opening and closing brackets. That's because we have time type.h in the same directory. It's not going to have to go search there. It finds it faster, and it also resolves conflicts. For example, if you redefine time type, I'm trying to see that. It's towards the end. We were at the end of this lecture. That's a very good question. I forgot to mention it, actually. If we see the quotation marks used, it'll find it in the current directory and it won't look for it anywhere else, which might actually help you, because if we have multiple time types, then it will use the first one it finds. Here it is here, in the current directory, instead of going into the include directory, because there may actually be a case in which you've used a name that might be part of a library file. But here we're locating them all together, and it's actually, in terms of the standard, it's quite common to see the .h's with the .c++'s all together, and not to move them all over the place. Because then, if you're looking for the implementation versus the specification, you can find them all in one place. It makes it easier to resolve. So that was a very good question, actually. Are there any other questions, good or bad, or anything? Yeah?
In the previous class, you were like the return type of the function that was specified in the class. She was like character array.
Yes.
Is it like you can define even like a string? Is it same as the character array?
The character array and the string is an implement. This is the interesting thing. So C never had a string class. String.h is a class. And C had character, and in order to make a string in C, you had to do a character array. And so character array is actually equivalent to a string, because the implementation of the string class method that creates the string, the default constructor, actually implements a character array. So you can actually use a string and a character array and intermix them. You can say string. And actually, if you're familiar with character arrays, we know we have index values, 0, 1, 2, 3, all the numbers, all the characters. You can create a string object, string space my name, or name, and then go name, and then opening and closing brackets, put like a 0 in there, and get the first character, 2, get the second character, third character, and actually treat the string as if it were a character array. They're identical. If you're going to use a character array, you have to specify the size of the character array, and that sets the size of your string. I believe that was in the first part of that lecture 3 that I showed you. And if it's empty, it will automatically set the size on its own. If you specify the size, we're going to talk about arrays actually coming up. If you set the size using the character array, it will take the string that you assigned to it and dynamically allocate the size for you automatically. Or you can set, here we have 255. That's a pretty big array. So we can hold any size. That's kind of wasteful, actually. But this is not using the string class, assuming that you don't know about it yet. If you use the string, then you have to include string.h, and then you say string space name. So, and string is actually capitalized. Is it capitalized? I believe it should be. It might be lowercase, actually. It might be lowercase. It kind of breaks the rules in terms of what I said about capitalizing the first character of the name of the class. I believe it is lowercase. I believe it is, which makes it seem like more of the data types. And that's an inconsistency, actually. It is case sensitive, I'll tell you that. I believe it is lowercase, because all the other data types in C++ are lowercase. But when you create a new instance of it, it'll automatically, the string will automatically set itself as if you were to say character name, leave this empty, equals some string. It will actually assign the correct character array length, which is that's what the default constructor of the string class is actually doing. It's the same implementation. So they created the string class because, well, you know, it's easier to use a built-in data type, which doesn't exist, to create a string character array. So, yeah, we're going to talk about, we'll look at the string class because it has methods and things, and we actually saw one of the methods today, the string copy. And yeah, that's one of our future lecture topics. So we'll just get out early today. How's that? So okay, and we'll talk about inheritance next time. Because if you're I don't know, if you've done this in Java, this is boring. If you haven't done it at all, this is way too much information for you for one class anyway. So I'm trying to get a happy medium between the two. So okay, so we're done for today. So, and we will have class next week. We will. So the Monday